In this video we're going to talk about exponential functions, and we're going to look at some of their basic properties, their graphs, and how to evaluate them. Okay. So let's start by talking about what we mean by an exponential function. An exponential function with a base a is of the form f of x equals a to the x, where a is a real number, a is greater than 0, and a doesn't equal 1. These last two conditions we have for a couple of reasons. So we take a to be greater than 0 so that when we talk about transformations of functions, things like reflections and shifts will make sense. And the reason we take a not to be 1 is because of the case if f of x is 1, a is 1, we're just looking at the function 1 to the x. And here we can see that no matter what we put in, this is always just going to be 1. So here we're just looking at a straight line, and it's not a very exciting case. So we'll take our base not to be 1. Okay. Examples of some exponential functions. Here is just a general example of an exponential with no shifts or transformations. So f of x equals 3 to the x. And then we can see some of the other types where we actually throw in some of those transformations. So we've got some reflections, some shifts, some stretches, again some reflections, and here some vertical transformations. Okay. So these functions will work just like all of the other functions, the polynomials, the rationals, our absolute values, all of those basic functions we've talked about up till now. Okay. So to evaluate an exponential, again, we're going to do things very similar to what we did for some of the other functions we looked at. So if I give you f of x equals 4 to the x, and I want to evaluate these different values, again, that just means I'm going to plug into the value for x and then simplify. So f of 2, in this case, would be 4 to the second power, which we can see is going to be 16. If I look at f of negative 1, looking at 4 to the negative first power, here we can use our properties of exponents to rewrite this as 1 over 4 to the first, or 1/4. At 0, we're looking at 4 to the 0. Again, we can see some of our basic properties there. So 4 to the 0, remember anything to the 0 power is just 1. And then to the half, here again, going back to our properties of real numbers, this is the same as the square root of 4. So we'll get a 2. And then lastly, 4 to the negative 3, we can see this is again going to be 1 over 4 to the third power, and we can simplify there to 1 over 64. Okay. So a couple things to notice about all of the values that we picked here. First, all of the values came out to be positive numbers. So notice it doesn't matter whether I put in something negative, or something 0, or something positive. All of the values come out to be positive numbers. The second thing to notice is there's no restriction on what we plug in for x. So again, I can plug in positives, negatives, and zeros, and all of them can be evaluated. So these properties give us some nice information about the graph. Okay. First off, the fact that we can plug anything in for x tells us that our domain is going to be all real numbers. The values coming out to be strictly positive tell us that our range is going to be from 0 to infinity. And our y-intercept, again, when plugged in x equals 0, gave us a value of 1. In general, if we look at f of x equals 4 to the x, we can plot those values that we found on our graph. Now some of them are not going to be as easy to graph because we got some interesting fractions in there. And again, if we pick some more values, we would see that some of them are not going to be as easy to plot as some others. So you've got to kind of pick and choose. Some of the nice ones that we had, well, when x was 2, we got a value of 16. At 0, we got a value of 1. At negative 1, we had a value of 1/4. Negative 3, we had 1 over 64. That one's probably not going to be so easy to graph. And if we just look at those, what we see is it's going to get bigger to the right and slowly get smaller to the left. Smaller, but still positive. Okay? So there would be our sketch for f of x equals 4 to the x. Okay. So in general, we can make some conclusions about the graphs of exponentials. And I would encourage you to do kind of what we just did for other things, like f of x equals 2 to the x, 3 to the x. Then throw in some of the fractions, 1/2 to the x, 1/3 to the x, and just see what your functions look like. So these two things I'm about to say will make a little bit more sense. In general, if I'm looking at f of x equals a to the x, where a is bigger than 1, so this is the example kind of like what we just did. You'll notice the domain, range, y-intercept are all what we just said. All real numbers, 0 to infinity, and 0, 1. One thing I didn't mention, but we can certainly see on this last graph, is that as x goes to negative infinity, the y values get closer and closer to 0. So we end up with a horizontal asymptote at y equals 0. And generally, for this case, if my a is bigger than 1, then my y values are going to get bigger as I move to the right. And so here, if this is my value of 1, we can see for a general exponential graph, a being bigger than 1, I'm going to be looking at something that looks like this. The value a basically tells me how quickly this function is rising. So when I move 1 unit to the right, I'm going to go a factor of a, up. Meaning when I'm over here at 2, I'm going to be up here at a squared. Okay. And likewise to the left, it just says when I move 1 unit to the left, I'm going to be at a factor of 1 over a. Okay. And again, you can think as I move further out, the values are going to get less and less by factors of a. Okay. If we look at the other side of that, meaning if my a is less than 1, and notice here I put that 0 less than a less than 1, because remember your a value is always greater than 0. So here I'm looking at fractions, small numbers between 0 and 1. In this case, notice a lot of my information is still the same. I'm still looking at all real numbers for the domain. The range is still 0 to infinity. The intercept is still 0, 1. And my horizontal asymptote is still y equals 0. The only difference is my function becomes decreasing. Okay? So again, if this is my value 1, instead of moving upward to the right, my function is going to go downward to the right. And again, that just means as I move towards the left, my values are going to increase by factors of a. And as I move to the right, my factors are going to decrease by factors of a. Okay. Again, as it goes to positive infinity, the function is going to go to 0. So let's look at some transformations of functions, because our exponential functions are going to work just like the functions we used before. If I'm trying to transform them, I'm still going to have vertical shifts and horizontal shifts, reflections, shrinking and stretching, and all of those other things we've talked about before. Okay? And they work very similarly. It's just some of them aren't as obvious on the graph as we would see with the exponential. Okay? So first let's consider f of x equals 2 to the x plus 3. Okay? So here we can see my basic function is f of x, or I'll just call it y equals 2 to the x. And so our transformation here is just the plus 3 in terms of the x, which is going to shift it left 3 units. Okay. So here, let's start by looking at just the basic curve. So y equals 2 to the x. Again, we know that there's an intercept at 0, 1. When x is 1, we can see that it's 2. At 2, it's going to go up by a factor of 2, so it'll be at 4. At 3, it's going to go up by another factor of 2, so it'll be up here at 8. On the left, it'll be at a half, then a fourth, and so forth. So there would be our y equals 2 to the x. Okay. So shifting it left 3 units, again, just means I'm going to take all of those points and move them to the left by 3. So this point that was at 1/4, if I go over 3 units, that's where it's going to end up. The 1.5 at 1. Here, our point at 2, at 4, and up here at 8. Okay. So we're still getting the same curve, still same shape, I should say. Apparently I can't draw straight lines through points. There we go. So same shape, just shifted over by 3 units. Okay. All right, let's look at another one. So here let's consider 1 minus 2 to the x. Okay. So here again our basic curve is still y equals 2 to the x. But now if we look, we've got 2 transformations in here. So the first is this negative out front. So remember here, because 2 to the x is our original y, the negative is going to reflect it about our x-axis. Okay. And then the 1, well, we can think of that as negative 2 to the x plus 1. So it's also going to shift up 1 unit. So a couple of things to keep in mind here. If you remember your domain and range and your asymptote, those things are also going to be affected whenever I've got vertical transformations. In this last case, because it was just a horizontal transformation, one thing to notice is that horizontal asymptote, that was at y equals 0, hasn't moved when I shift left and right. Okay? So for the black curve here, the horizontal asymptote is same as the red curve. Over here, because I now have a vertical transformation, that horizontal asymptote is going to be affected. Okay? And again, it does make a difference what order I do these. Okay? So here I can think when I take my values for 2 to the x, so I'm going to do those here in purple. So same points we had for the red curve on the last one. So there's our y equals 2 to the x. Okay. when I start by reflecting, I'm going to reflect it over the x-axis. So instead of having an increasing function, it's going to change to something decreasing. Okay, so this would be y equals negative 2 to the x. Okay, notice for both of these curves, the horizontal asymptote is still the same. Okay. And then lastly, to move that up 1 unit, well, all of our values are just going to move up by 1. So our intercept that has now been shifted to 0, negative 1 is going to go to 0, 0. Our point that was at 1, negative 2 is now going to be at 1, negative 1. Our 2, negative 4 is now going to be 2, negative 3. On the other side, our point that was negative 1, negative 1/2 is now going to be negative 1, positive 1/2. So it's kind of going back to where we were there. And our point that was at negative 2, negative 1/4 is going to go up to positive 3/4. Okay? So notice our asymptote has moved. Okay? So instead of it being here at y equals 0, the asymptote is going to be affected by this vertical shift. So over there at y equals 1 becomes our new asymptote. And we can see as we move kind of to the left on the curve, our values are getting closer and closer to y equals 1. Okay. So there's a sketch of our graph, and you can kind of see the different transformations on that one. Alright, let's look at one last one in terms of the graphing. So here let's consider f of x equals 3 times 2 to the x. So again, basic curve is still y equals 2 to the x. Our transformations, if we look, there's only the 1. We have the 3 outside of the function, so this means I'm going to either stretch or compress. Because it's outside of the, with the y value, we can think this is a vertical stretch by a factor of 3. Okay. So here, this is going to change very quickly, so we'll just do a couple of the same points. So at 3 we were at 8, 2 we were at 4, 1 we were at 2, 0, a half, a fourth, etc. So here is our y equals 2 to the x again. Okay. Now if we look at the transformation, stretching by a factor of 3, that means I'm taking the y values and multiplying them by 3. So here, if I'm looking at my intercept, instead of at 1, it's going to be up here at 3. The value at 1, which is 2, is going to go up to 6. The value here at 4 is going to go up to 12. And so forth. So the one at 8 is going to be way up there at 24. On the other side, I'm still going to have positive, and the difference is it's not stretching it more negative like it would have with the other functions. So here at 1/2, notice if I multiply that by 3, I'm looking at 1 1/2. If I look at the 1/4, I'm looking at 3/4. Okay? All of my values are still positive, and my horizontal asymptote is still going to be at y equals 0. So the stretching it doesn't change that. Okay? The only thing that's going to change is how quickly my values increase and decrease. Okay? So there is my graph of y equals 3 times 2 to the x. Okay. The last thing to mention about exponentials is what we call the natural exponential function. Okay? And this is useful for a lot of the applications that you're going to see both in this class and in later classes. The natural exponential is a exponential function of a particular base. And so here, I want to just have you think about something for a second. If you remember your compound interest, there was an expression that looked something like this. There were some other things in here. We had a P and a T up here, and it was to give our total amount in an account at any time. And if you don't remember that, that's okay. You'll see it again when we talk about our modeling. But this expression in particular was very interesting. R here was assumed to be our interest rate, and N was the number of times we compounded. And I want you to look at this expression because I want you to think about what happens to this expression as my N values get big. Okay. Why the N values? Well, again, if I'm thinking about the number of times I compound, I can increase that indefinitely. So I can think I can compound once a year, so N would be 1. 3 times a year, N would be 3. Maybe I want to do it monthly, so it's 12. But then I could also do every day, so that could be 365. So as you can see, this number can get bigger and bigger. But because the number is not just in the base, it's also in the exponent, this number is increasing in kind of an interesting way. And it does it exponentially. And what we find is as this number gets really large, by really large I mean like 10,000, a million, 10 million, a billion, etc., keep getting increasingly large, what we find is as that N value goes to infinity, this number gets closer and closer to our transcendental number E. And for those of you who are watching this video who have never heard of E, if you plug it into a calculator, is an irrational number that's about 2.71. Okay? It's useful for a lot of what we're going to do in terms of exponents and logarithms, and again, like I said, for a lot of our applications. And the reason I bring this up is because you are going to be asked to do a lot of things with base E that you were asked to do with our other exponentials. Okay? So for example, if I said graph the function f of x equals e to the x, we're doing very similar things to what we just did with our 4 to the x and the 2 to the x. The only difference is the base is not a pretty number. Okay, so here if I wanted to graph this function, e being about 2.71 says my base is greater than 1. So I know it's going to be increasing. I still have y equals 0 as my horizontal asymptote. And again, when I plug in 0, I'm still going to get a value of 1. Okay, so here, sketching my graph. At 0, I'm at 1. At 1, I'm looking at e to the 1 power, which is about 2.71. E squared, well, that gives us about a little less than 8. On the other side, 1 over e is about 0.2. And I'm not even going to try to go further. You can look at some calculator values for the lower numbers. But there we can see it's still a basic exponential increasing to the right, going to 0 to the left. The only difference, again, is the values that we're looking at in between. They don't turn out to be perfect integer values. Okay. So for this section, you're going to see a little bit of, shifting e to the x. Again, for those values, you can approximate them. Later on, like I said, we're going to use the e to the x, or the e function, so to solve applications and also to use for our logarithm.